Hola clase, today we are going to learn how to work with DeMoivre's theorem. And as usual, I could give you a how-to step by step, and then we'll make an example together. Now, I need to know the theorem itself, and we're not going to prove it. That is in another video, but it's telling me that if I've got a complex number in polar form, then I can get the nth exponent of that number by doing r to the power of n cis of na. What this is telling me is that complex roots of one equation are actually equally spaced in the complex plane. So they are making, or they are points, better say, within a circumference equally spaced in the complex plane. Now, the use of this, the actual beauty of that, is that if this is true in one way, it's true in another. So if now I've got a complex number that is actually the nth power of a number, I can get the original, because that could be this whole number to the power of 1/nth. That's how I could get rid of that nth. Or to all effects, by what we know of trigonometry, that could be r to the power of 1/nth cis of theta plus 2 pi k divided by n. And this allows me to get all the complex roots of an equation. Now for the how-to step by step, now you need to remember that this works if you're working in polar form. So if they don't give it to you in polar, you're going to have to do it. And then you're going to substitute in the inverse form of the theorem, meaning in here, r to the power of 1/nth cis of theta plus 2 pi k over n. And with that, then you can obtain all the solutions. They're going to have the same modulus, but the argument is going to be different. And for that, what you need to do is to substitute k starting from 0 all the way to n minus 1. Now let's see that in an example. They ask me to solve this equation here. And in this case is in terms of n. Okay, so the very first step, it's taking this set to the power of 5 that they're giving me here as a rectangular form. Remember, this, it's multiplying the imaginary constant, so that would be a b, and turn it into polar. We're not going to go on to the how-to, we've got a video for that, but if I do that, this 243 is 3 to the power of 5, by the way, so that could give me a modulus of 3n to the power of 5 and an argument of 3 pi halves. And for that, if it's one case like this, you know that it's actually purely imaginary, so you can convert very straightforward. Now, once I've got that, I can get z, because z is going to be now 3n to the power of 5 c's of 3 pi halves, all of that to the power of 1/5. And if we do that, that's actually very good for the argument. It simplifies, and then c's of 3 pi halves plus 2 pi k, all of that divided by 5. And now it's a matter of here beginning to substitute values of k, starting at 0 and going, in our case, all the way to 4, because when I've got a 5, it's going to cancel here and we're going to end in the same place. Okay, if we start there, the very first one, k equals 0, that would give me 3n c's of 3 pi tenths, and it's coming from simplifying these two there. So this, let's put it here, k equals 0. Now I'm going to do the same with k equals 1. The modulus is going to stay the same, but now I'm going to have 3 pi halves plus 2 pi times k is 1, all of that divided by 5. So now I'm going to have 3n, that hasn't changed, but now it's going to be the c's of, if I move this here, it's going to be 7 pi tenths. Now if we do the same with k equals 2, now 3n, that doesn't change, and then it would be the c's of 3 pi plus 2 times 2 pi, which could be 11 pi tenths. If we do the same with k equals 3, then we would have the c's of 15 pi tenths. And I'm sort of going to run out of space. If we do the last one, I'm going to put it here. That could be 3n c's of 19 pi of 10. And all of these are the solutions. There are 5 solutions there to one equation. So I'm going to box them there. And once we have them nice and tidy, we're done. Okay, so now it's your turn to practice. Thanks for watching.